And now, very excited to hear how we're all going to abandon Python for Julia instead. From Fredrik and Kristoffer. Go ahead.
So thanks for the introduction. So I'm here with my colleague Fredrik. We work for Julia Computing, and we will talk a little bit about Julia for AI and data science. And for those who don't know, Julia is an open source programming language. You can just download it and start using it straight away. It was released around 10 years ago, and right now it's at version 1.7. So I mean, there's no more breaking changes being done. So if you write code in it now, it should keep working for a long time. But I'm guessing many of you haven't really seen Julia code before, so I thought I would just put up a little bit of Julia code here to look at. So here first I'm defining a struct, sort of an aggregate that can contain some other data, here a radius. And then I define an area method that takes a circle here and computes the area. So here you can already see a little bit of a difference from, for example, C++ and Python and Julia, where in Julia you have data and functionality separately, so you don't have classes. So Julia is maybe a little bit more like C in that sense. And then I define another struct, a rectangle here, that has two fields in it, width and a height, and another area method that takes a rectangle this time, computes the area. Then I can create a vector of these shapes, so I have two rectangles and a circle here. And I can compute the area of all these shapes. And here I'm using a little bit of syntactic sugar. If you see, there's a little dot here in front of the function call, and that means that you're applying the area function to every element in the vector. So one thing I want to mention is sort of genericness about Julia. So here I just define a function here, x squared plus x, and I can call this function with an integer, a float, maybe a complex value, a matrix, or I can load a package here. I load a package called forwarddiff, which does forward mode automatic differentiation. And I can call this f function with this dual number here. So with the same function, I can call it with many different types. And just an interesting note here, the reason there's a 7 here is because if we take the derivative of this function, we get 2x plus 1. And if we insert 3 here, we get 7. So the derivative of this function will end up in this dual component there. So it's just an interesting note here about how dual numbers works and how you would use them. So I'm guessing maybe I'll be the only one with slides here that includes assembly code. But I just want to show you here that depending on what you call the function with here, if I call the function with an integer, we can use this code native in Julia to see what assembly code is generated. And depending if I call it with an integer, a float, or a complex number, it generates a new specialized version of the function here. And all of these are pretty efficient compiled functions, and even for this number type that I got from a package, we still get efficient code. So basically for one function, depending on what you call it with, you generate instances of this function with a specialized compiled code in it. So one thing I thought about is what demands do AI and data science have on a language? And I would say that AI and data science pushes sort of the demands of the language to the max, and also the ecosystem, the set of packages the languages provides. So one thing we can talk about is performance. We have large data sets, so we need to be able to pack data tightly. We want to have good performance on both CPUs, but also GPUs and other accelerators. We want the language to have sort of a high-level feeling. We don't want to write kind of C-looking code. We want to write a short amount of code that does a lot of things. We want good language interoperability, so we want to be able to call C and Fortran. A lot of needed stuff are written there, but maybe we also want to be able to call Python and R, which also have a lot of good, useful code in it. We're going to have requirements on package management and the package ecosystem. For example, machine learning toolboxes, good automatic differentiation. We want to be able to do visualization, plotting, and also maybe interactive visualization, tabular data, and so on. So quite a lot of demands on the language from this AI and data science point of view. So a little bit talking about trades-off in programming language. So here I'm focusing a little bit about performance, but typically you could maybe divide languages a little bit, like you have languages that are compiled, which are considered fast, versus languages which are interpreted, which might be considered slow. You have low level versus high level, static versus dynamic, and so on. And if you want to take two sort of extreme cases, then maybe you could put C on one side and Python on the other side, where C is sort of low level and fast, and Python is very high level, but maybe a little bit slower. And a little bit of a claim here is that if you have a sort of a slower language, you are going to need significant support from a fast language, which this is sometimes called the two-language problems, because there are cases where you need the absolute best performance. So just took an example here. If we look at NumPy and SciPy, very popular Python languages, you can see that they have quite a lot of Python in them, but they do also contain quite a lot of Fortran here in the case of SciPy, or C in the case of NumPy. So you need this sort of lower level language to support the high level language. And a little bit of an idea about Julia is sort of to limit the dynamic features a little bit, so you can still do like proper compilation and get this native C-like speed, but it should still feel like high-level dynamic and kind of feel a bit like Python. So if I look a little bit on the Julia package ecosystem here, I took a bit of these different categories, and I looked at sort of the most popular packages. And what's common among these is that all of these, if you look at what they're written in, they're all written in 100% Julia. So this shows to me a little bit that it is possible in Julia to not have to sort of go down to a lower level, faster language, but you can fully write things in Julia. So why does this matter then? Well, I think there are a few perks that come when you have one fast language. So for example, it creates a smaller distance between what's sort of known as developers and users, because they share the same language, they share the same tools, and I think that increases sort of collaboration. You don't have these sort of developers that works on maybe the low-level code and the hard stuff, and the users who are sort of using their stuff. There's more of a shared environment there. I would claim it increases productivity a bit, because you don't need to learn this second language when you figure out like you've written a lot of code and, oh, I need it to be faster. And maybe the only way is to then go down to the lower level, faster language. Not having to do that can be a bit of a productivity boost. And you can also do things like you can step through everything with a debugger. If you have two languages, it's hard to step into the second language with a debugger. And there's also some performance considerations. So typically, when you use sort of maybe MATLAB or NumPy, you talk about this vectorized code where you're calling sinus on a big vector, then you call cosinus on a vector, and then you add those two vectors and so on. So you're not doing this small scalar operation in your native language, but you're trying to do this vectorized style. Well, if you have a fast language, you don't have to do this sort of vectorized thing. You can just write a loop with scalar code. And it's also hard to, for example, inline higher order function through a foreign interface like that. So if you have a sum, but you want to mutate the elements in some way here, it's hard to inline this function, for example, if you have two different languages, if sum is written in C. But I would say the most important thing is sort of composability, and I will try to give a short example of that. So here I have an example where I load a package that contains sort of a vector, can represent velocity. And there's a planet which has a mass and a velocity. I can compute the energy of a planet, and I can compute the total energy of a vector of planets as you sum the energy over all the planets. And here I create a vector of different planets here. And first we can look at sort of the size of this vector, the memory. Well, we have 3 planets, and each planet has 1 8-byte float there and 2 8-byte floats there. So 72 bytes. So with that, I want to say that things are stored efficiently in memory, just as sort of the data. There's no overhead there. And we can compute the total energy of the planets there. And then we can sort of benchmark this. I can load a package called benchmark tools and do a benchmark. And it takes about 40 nanoseconds to run this on these. But now let's say I want to run this on the GPU instead of the CPU. Well, I can just load the CUDA package there. I can transfer from the data from the CPU to the GPU. And here there's a typo. It should be planets_CUDA here. It just says planet. But I can just as easily run this code on the GPU without having to change anything. But let's push this compressibility a little bit further. Now, if we go back and we look at this, for those people who come from a physicist background, this is quite awful. Like, what are these numbers? What do they mean? What's this velocity? Is it in meters per second, or what is this? So let's load another package. It's called unitfull. And with that, we can sort of start adding units to our codes. So here I'm going to say that the type of this mass is some sort of mass. I'm going to say that the type of this velocity is some sort of velocity. And now when I create my planets here, I can add kilograms on the masses, and I add kilometers per second here on the velocities. And we can see that the size of the planet vector is the same as before, so we don't pay anything in space for this. And now when I compute the total energy here, we get it with units here. And I didn't change any of my code. And I can compute the total, I can convert this unit, let's say, to gigajoule, and then I get it in gigajoule instead. And if we benchmark it, we see it takes, I think it was 39 nanoseconds last time, now it's 40, so some noise there, but it doesn't cost anything in terms of performance. And at the same time, I can convert it to a GPU array and do the computation on the GPU. So here I would say I have 3 independent parts. I have the unit part, I have this vector part, and I have the GPU part. And all of these, none of these know anything about each other, but still they can sort of compose together to create one result without having any overhead in space or in performance. So I will leave that over to you now.
Thank you. So I will bring this example of composability into the domain of scientific machine learning. So scientific machine learning is maybe the combination of science and machine learning, one for the other for one. And in science, we often talk about differential equations. And I will step you through an example of solving a differential equation and see where composability comes into play when we're doing this. So the example is a very basic pendulum. And to solve a differential equation here, we load the package differential equations, and we load a plotting package also. And then I define the dynamics. So that's a standard function definition. It contains 2 equations. Here we have an equation for the force, and you integrate that, you get the velocity. You integrate that, you get an angular position. I define some parameters, gravity here. This was defined close to the equator. We have a length, we have an initial condition, and then we package that into a problem structure we call solve. So that's not very controversial. Then I call plot, and the plotting function from plots understands how to plot the solution because there is a recipe system that tells the plotting functionality how this structure sol should be plotted. And we get something that swings back and forth, and it decays slowly because there is some friction. Now, composability comes into the picture. In science, we are often uncertain about our models, and we should be honest. We should compute with uncertainty. We should also tell people when we publish our papers about the uncertainty in our models. And if we want to now introduce, maybe we have some uncertainty on our parameters. The gravity is slightly uncertain because it varies across the surface of the Earth. We might have uncertainty in the initial condition and so on. And the difference we make to our code is very minor. I load another package, Monte Carlo measurements. It contains definitions of types that represent uncertainty in numbers. Crucial and a key point here is that I didn't change the definition of the pendulum. Also, I certainly don't change the definition of the ODE solver that integrates this differential equation. What I do change is the definition of the parameters here. I add plus minus some uncertainty here. And I do that to all my parameters. I solve it again, no change here. And the plotting package once again understands how to plot uncertain numbers. So now there are uncertain numbers inside the solution, and we get some ribbons on our plot indicating that in the beginning there is very little uncertainty, but as time goes by, the frequency of the pendulum is slightly uncertain due to the uncertain length. And if we continue this after a while, we have no idea about the state of the pendulum. So this was very simple to do, and I argue in science we should always do stuff like this. It should be convenient, preferably. Otherwise people will not do it, even though maybe they should. So once again, I will flip back and forth between this slide and the previous slide. The amount of change you need to do to accomplish something like this is quite small. And if it's accessible, people might be more likely to use it. I will extract the equation for the force in the pendulum. We have it here. So we have a call to the division operator, multiplication, and a call to the sine function. And sine of theta here works no matter what type theta has, as long as there is a method for sine that accepts that type. So it could be a standard floating point value, but it can also be an uncertain value like we saw. It could be a symbolic value from a symbolic toolbox. It could be a dual number for automatic differentiation, or it can even be a matrix because sine is well defined for matrices. If we contrast this to how we would probably write this in Python, we will run numpy.sine, and that function only understands floating point values. If we try to send symbols in there, it will complain. So if we want to support symbolic functionality in the code we write, we need to kind of maintain a separate code that uses sympy.sine instead. And this composability extends through the entire language. So the ODE solver that integrated the dynamics. It's composed of multiplications and subtractions and probably not many calls to sign. But as long as all of these operations are supported by custom types, the ODE solver will accept them and propagate the dynamics. And the same goes for these dual numbers. You can take derivatives through your ODE solvers, and that just works without any problems. You can run it on the GPU as well. So here is an additional example just to drive home the point. I have defined a trigonometric identity. You might be familiar with it. If I send in a floating point value, you get the number of 1. If I send in the uncertain value here, I get also the number 1. And there is no uncertainty left because it doesn't matter what the number is. The identity is always 1. And here we actually send a random matrix in. The result is an identity matrix, so that works. We can define a symbolic value x. We get a symbolic expression. It looks identical to the function definition. But if we perform symbolic simplification of that, we get number 1. So that works as we would expect. And the symbolic functionality is actually quite powerful. You can trace through arbitrary Julia code usually and get symbolic expression that you can do further computation on and maybe change the behavior of your program if you would like to. And how does this extend to machine learning? So a common task in scientific machine learning is to learn something about the system you are observing data from. So let's pretend for a moment that we didn't know the dynamics of the pendulum, but we did know some structure. So we know that we should integrate once to get the velocity, and we integrate twice to get an angle. But we maybe don't know the structure or the expression for the force that acts. Maybe the friction is complicated, or there is some complicated air resistance or something like that. Then we can stick a neural network in here that has some parameters, and it takes the states and it computes the force. And in Julia, you don't need a special machine learning library to solve this differential equation. You use the standard differential equation library. And that library is state-of-the-art for scientific applications, normal solving of differential equations. And that is a key strength of the Julia ecosystem, that if you have to write a special ML solver for differential equations, that is probably not going to be what you go to if you want to solve a traditional ODE, because it don't have all the options, it doesn't have callbacks, it's not fast, it doesn't have the particular ODE method you will want to use for your particular science problem. And that's a problem then, because if you need to use a special ML solver, that might be 100 times slower for scientific applications, because scientific application might be very large. You might have 10,000, 100,000 states. And you might have structure in your problem, and you need to exploit that structure, otherwise it takes way too long to solve it. So in Julia, you can use the differential equations package and do all your machine learning using that. There is a package called diffeqflux that defines the stuff you need to take gradients through all of these solvers. There are hundreds of solvers. They can solve all kinds of different problems. So we have ordinary differential algebraic equations, partial delay differential equations, stochastic differential equations. They are all represented there, and you can solve problems with them in a machine learning setting. And of course, you can use automatic differentiation with them. You can compute on the GPU. You can stick units in there. You can propagate uncertain values, all while taking gradients through the solvers. And nowadays, actually, a lot of development on differential equations take place in Julia. So state-of-the-art solvers are often nowadays implemented in Julia and presented at conferences as Julia packages. And they routinely benchmark faster than the previous state-of-the-art, which used to be Fortran based.
So to summarize a little bit, we claim that Julia is sort of a high-level dynamic language, has a C-like runtime performance. The Julia package ecosystem is mature. It has the core packages available that you need for an AI and data science workflows. And having the ecosystem to be sort of completely in Julia gives many benefits. There's performance, but also these composability aspects.
Yeah, and I hope we showed a very brief introduction of why composability that works in practice can actually enable a lot of powerful features, more or less for free, where you can write code that is agnostic to all these features, but it works even though you didn't put an effort into making it work. And scientific libraries in Julia, they work for the standard traditional science where you just solve the equations, but they also work for the machine learning application where you need to take gradients and estimate parameters and stick neural networks into places where you don't know the scientific structure. All right. Thank you very much for us.
Take the next slide.
Oh, sorry.
So yeah, thank you. I put our emails up there if you want to contact us. We're also available on the Julia Lang Slack. And also Julia Computing is hiring. So if you're interested in working with AI, data science with us, they put a link to our jobs there. So yeah, thanks.
So, thank you. Do we have any questions from the audience? Okay, Jesper. So while waiting for them, okay, starting over there.
Hey. It looks so neat. I really love the units. I would have loved that, especially back in my physics days. But I'm wondering, are there any drawbacks?
Yeah. One drawback could be
compared to Python, maybe that sort of.
One drawback could be compilation time a little bit. Like if you're, as I showed, when you're compiling specialized code, high-performance code for a lot of different types, then there is a compilation time cost involved in it. So that's one way. And if you're trying to stack like very many different things like units and uncertainty and so on top of each other, there can be some issues cropping up there where somehow they are incompatible. So, but in many cases it works pretty well.
Thanks.
Thank you for the talk. So I don't know anything about Julia, so I'm sure it's obvious questions for anybody who's know even briefly about it. But so what about portability and the compiler? Is it its own compiler, or is it a front end to LLVM, or how does it work?
It uses LLVM, so it translates Julia code into LLVM IR, and then it runs the same optimization pass line as Clang would do or Rust would do. So that's sort of how it piggybacks on all the performance stuff that's been done on LLVM. Okay,
so in terms of portability, you still have support for a pretty wide
variety.
Yeah,
it runs on Windows, Julia, Mac, and all the standard stuff, FreeBSD, and the stuff that LLVM sort of supports.
Right. Is LLVM also using CUDA? Can it compile to CUDA?
Yeah, that's what I showed. When we're loading the CUDA library there, it's sort of piggybacking on the Julia compiler to compile Julia code, but then instead of targeting your CPU, it's targeting the GPU.
So LLVM is doing that?
Yeah.
Okay.
Thanks very much for the talk. I was wondering about when you read about Julia and when you look at talks and stuff like that, there's a lot of information about how you work with it in the interactive way. What about using it as a standalone component, like in a microservice? How do you support that?
Yeah, I don't think any of us have experience with that really, but people do use it. There are some nice examples. A company called Relational AI that hosts it's a relational database, and they have quite a large number of customers that actually do this, and they typically host their code on some Amazon Web Services or some cluster and offer everything as a cloud-based software as a service and stuff like that. I can't give you much better answers than that, unfortunately.
Okay, thanks.
Yes, one question about TPUs. Does Julia support TPU, and what about edge devices?
TPUs. There used to be a package called xla.jl, which sort of was used to target TPUs. I think that has bit-rotted now. So I'm not aware exactly of what the state is right now when it comes to TPUs, actually. So I'm not sure.
Thank you.
Yes. Here.
Yeah.
I really liked the probability implementation. I guess that was just a simple plus and minus value. Probability can go much deeper than that. Did you think about first simple Gaussian distribution and or own probability density functions?
Yeah, so the package I made use of here, Monte Carlo measurements, it actually represents the probability distribution as a number of samples. So you can have any arbitrary distribution in that case, and even multivariate distributions. And all the caveats that apply to Monte Carlo sampling obviously apply to that example. There are other packages that do similar things. So if your distribution is actually Gaussian, you can do uncertainty propagation by linearization. There are caveats to that also, of course. You can use something called polynomial chaos to represent probability distributions. There is a package for that also. It has different trade-offs. So uncertainty propagation in the most general case is quite a complicated and hard to solve problem. Monte Carlo propagation gives you a nice answer with limited computational effort, but it doesn't give you a super precise answer. So if you want super precise, you need to spend a lot of effort. But,
Thank you. A really good answer. And here, I'm glad to hear that there are much more advanced methods than the simplest ones.
Yep.
So thank you.
A follow-up question on that. So Monte Carlo usually specify warm-ups and sampler and number of samples and so on, and that was not part of the code.
No, that is a different problem. Then you do inference using Monte Carlo sampling. This was just propagation. So if you have a probability distribution of a parameter and you do some computation of that, and you want to see what's the probability distribution of the result, there is no sampling involved. There is just sampling when you sample from the initial distribution. But if you try to infer the value of a parameter based on observed data, then you come into where you use Hamiltonian, Monte Carlo, and stuff like that. Yeah.
Okay. Need to learn that. More questions?
Hi. I have a question regarding PyTorch. So I'm very used to using PyTorch for developing research in machine learning. Could you give some insight into the pros and cons compared to what Julia could offer me?
Sure. So PyTorch has a huge amount of resources. So it has a lot of use cases very well covered and very well optimized. So if that works for your applications, that might very well be the right choice. But if you want to go outside of the cookie cutter solutions, where there is not a cookie cutter for your problem, you need to make something custom, then it might be slightly harder. If there is not a very well-performant PyTorch kernel and you need to write it yourself, your choices are terrible performance or drop to C or Fortran. And if you are able to do that, that is great. Many people, especially scientists, are not trained to do that, and then the choice is much harder. And you might not really know what to do. Maybe you will just skip doing that interesting thing because you don't know how to do it.
I do have a bonus slide that I want to show, which is language interop. And I just want to show there's a package called pycall.jl. And with that, you can load the package, and then you can basically call into Python. So just an example here, I load the package, then I import the Python math library and the SciPy optimize, and I can define a Julia function here, but then I can call the Newton function inside SciPy with my Julia function to just use, if there's a really good algorithm in Python, but I want to use my own Julia function to sort of optimize it or something, I can just call it straight away. So there is pretty good interoperability with Python from Julia. So let's say you want to try Julia a bit, but you have your nice Python code, they can sort of work together pretty well.
You can go the other way also. And I think there is an effort to wrap PyTorch, so you can use it with a very nice and convenient Julia-esque interface.
Very interesting. I guess you would lose the composability? Because this wouldn't work with units.
Most likely. Right? What you can maintain is the ability to propagate gradients through. So there is an interface that if you start with some Julia code high level and then you encounter Python code, which is differentiable through PyTorch, gradients can propagate. So you can make that happen. You could make that happen for the uncertainty example here also, actually. But for a lot of other things, it would break there at the barrier between the languages. Yep.
Thank you.
Okay. We have time for one final question before lunch. Okay, so thank you, very interesting.
Thanks.